All right. Today we're going to be evaluating problem number 1 of homework number 5. Now, problem number 1's a little bit strange in that what it's asking us to do is redo the example provided by two different methods. Now, the example they're referring to is basically defined by this equation, z is equal to x plus y. What it asks us to do is actually evaluate the double integral based on this region on the xy plane. Now, there are two ways that the actual homework provides us to do this. One way is that it actually defines the domain on the xy plane first and foremost before going through the integration. Okay. The other way is that so we actually create limits on the integral terms that mirror this function right here and this function. These are one and the same, by the way. The other way it goes through is to say no, the better way to do is to evaluate the two variables x and y from negative infinity to positive infinity, respectively. All right, but specifically put in some sort of function, like a step function, a unit function, that defines the limitation of this term right here. All right. By doing so, we actually see we get similar results. Not only that, but I might be jumping the gun, but we actually show convolution of the terms. But let's go through it and show what I mean. Okay. So the first method that the actual homework goes through is to evaluate this double integration by first defining this domain. Okay. Now, of course, big F of z, our distribution function, can be defined as the probability of big Z less than or equal to Z, which, given this equation, we can substitute in. It's just x plus y is less than or equal to Z. Now that translates to this figure right here on the xy plane. As you can see, we can define all the x plus y below the line that defines x plus y, right here. We also define specific terms right here, like for instance on the y-axis equal to y, on the x-axis z is equal to x, as we can see. Of course, we can rearrange the terms if you want, which I put in here. It's like we can make y less than or equal to z minus x, x is less than or equal to y minus z. These are all ways to actually define the domain right here before we actually establish the integration. Anyway, when we actually do our integration right here, first we have this term right here. As you can see, we can rearrange things. We can define it several ways, okay? We can define our distribution, our big F of z in terms of z by first defining it on the y-axis, okay, in y parameter right here. And by doing so, we can see that we're evaluating from negative infinity to the z minus y plane. So as you can see in the figure, we start at negative infinity and proceed upward, 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 upward. And then in terms of y, this line is defined as the upper limit, which is z minus x. And then after we evaluate that integral, the inner integral right there, we can go on the work with the x variable from negative infinity to positive infinity. Equivalently, we could have looked at it the other way. We could do the inner integral be defined with the x term right here, in which basically, if we look, we're defining it from negative infinity, starting right here, all the way to an upper limit defined by this line, which is defined by z minus y. Okay, we figure that out. And then the outer integral defined by y, we find from negative infinity to positive infinity. Both of them are equivalent. When we evaluate the density function, I just decided to use this one, but I could have used either one. They'll give similar results. So one of the things we found that's kind of interesting is that if we look at, we find the density function, the little f of z, we figure that out by finding the derivative of this. So we take this term, just like I said, just pick this one. We can evaluate it. We can actually, this is just regular arithmetic, bringing over the terms. Okay. And this is just rearranging some arithmetic. We can see how we divided the d of z into two terms. These two cancel out. All right. This term right here is equal to 1. All right. And this term right here, this derivative, actually breaks down, and we can actually rewrite it as a term in terms of x by defining the function in terms of x, and substituting for y, we put z minus x. We can evaluate that term. And now, if we are given that x and y are independent, we can actually break this down, all right, into two terms. Little f of x in terms of x, and little f of y in terms of a substituted y function right here. All right. What we can do, like we said, we could actually use this term equivalently, and we'll get a similar result. It's just what we're going to end up with is a from negative infinity to infinity integral. It's going to be little f of x in terms of z minus y, and then little f of y in terms of y, dy. Okay, these two are equivalent terms. What it shows is that we actually have, I actually mentioned that right here. What that shows is that we actually have convolution of this term given this example right here. All right, so that's our evaluation via the first method. The second method specifically tries to avoid discussing anything, creating any limits here. It just looks at the entire plane from on the x and y axis from negative infinity to positive infinity, right here. All right. But how it actually handles the function is that in order to define things, it defines things in terms of the z function. All right, by creating by including a unit function and multiplying times our joint density right here. All right, and the way we actually define it, like any unit function, there's going to have to be a limit. All right, and we define it here as x plus y because of our equation right up here. All right. So what this means is that we're only going to be defining z's where z is greater than or equal to x plus y. All right? So if we actually do the arithmetic and just work this out, see, we can actually bring over the negative term, get this function right here, which we can arrange in two ways. All right? We can see it right here. We can rearrange this so it's put in z, we just put parentheses over this portion right here. All right. We also rearrange these two terms. It's okay. Okay. And what we're basically showing is that if we rearrange things in this manner, this is equivalent to actually putting in the limits using this unit function of putting from negative infinity to z minus x. Right there. All right. Which is equivalent to one of the terms we used up here, isn't it? Right there. Similarly, from this function, just using the step function, we could have just rearranged, put the y within the inner parenthesis. And this function actually breaks down so that the actual limits on the inside with regard to dx here's dy, we got z minus y, as you can see. These two are perfectly equivalent to one another. All right. If we actually break this down and actually find a derivative to get our little f of z, these two terms come out. They're equivalent. They correspond to these two. All right, and they also show convolution is existent if there's if we have the condition of independence is met, which I showed right here. So that's basically it. That's basically the two methods which are alluded to in the problem.